In example 3, we've got a piece of wire that is 24 inches long. It's going to be used to form a square and or rectangle whose length is 3 times its width. Determine both the maximum and minimum combined area using calculus. Okay. So I've got my wire, and we're going to bend it into a square and or a rectangle. So I'm imagining something like that, where you've got your ends and you're bending into a square and or rectangle. Okay, so on the square, we're going to label everything X. Then on the rectangle, the length is 3 times the width. So I'm just going to start by labeling them L and W, and then we'll get that constraint going in a second. So that's the kind of thing I'm imagining right here for step 1 and what the situation may look like. Okay, so my objective function, which is the second thing that I do after I'm starting to label some of my graph here, is to talk about the combined area. I find the objective once I know what I'm trying to maximize or minimize. It's the area, so that's going to be my objective. And so if I do the total area of this, it's going to be x squared, oops, I should write a equals for area, x squared for x times x, length times width for the square, plus length times width for the rectangle. And then our step 3 are constraints. Now we have 3 letters, we've got to get rid of 2 of them, there's going to be more than one constraint. So the first one is that the length, or the first one that came to my mind, you can put them in either order, is the length is 3 times the width. So the length is going to be equal to 3 width. Then the next constraint is going to be dealing with that 24 inches. That's going to be a constraint as well. So we have these 2 things for constraint. So that 24 inches has to go all the way around both of them. So that's going to be like perimeter. So all the way around the square is going to be 4x, plus all the way around the rectangle is going to be 2 length plus 2 width. And that needs to add up to 24. Okay. Now, I can use the first objective to replace L and get these in terms of L, get these in terms of X and W. Now, then I need to figure out what other letter to get rid of. I can solve for X and have it all in terms of W, or I could solve for W and have it all in terms of X. It doesn't matter per se, but if I divide everything by 4, these are going to turn into 1/2, and I'm going to have fractions in there. Whereas if I divide everything by 2, it's going to go in evenly. So we're going to solve for W and then not have to deal with fractions. So I'll have everything in terms of X. Okay, so let's do that. Let's solve for W. So the first thing I want to do though is actually, since I don't want L in here, is to plug this in here also. And then maybe our analysis will change. We'll see. So we have 4x plus 2 times 3w plus 2w equals 24. So 4x, that's 6 plus 2 is 8. Ooh, I'm going to change that. So 8w equals 24. Okay. All right. So it doesn't really matter if I'm solving for x or for w. I'm going to get a fraction. I don't know. Something about me just likes x. So I'm going to get a fraction if I solve for w. I think I'll just deal with it because I like x. So let's just deal with it. So we'll have our 8w equals negative 4x plus 24, and I'll have w then equals negative 1/2 x plus 3. Okay. So those are just the constraints. So the constraint lines that I need to use now, going back into the original, are the L constraint and the W constraint. I'm also going to use this W constraint twice because we have to plug it in for L. Cool. Okay, So we'll do that in our step 4. Okay, so I'm going to start step 4 over here. Try to keep my page organized. And so I have a equals x squared plus, the first thing I'm going to write is my 3w times w, or 3w squared. Then I'm going to put my w in, so I don't have to put it in twice. So that's a equals x squared plus 3 times now w is negative 1/2 x plus 3 squared. Okay. All right, and I think that's all for step 4. For step 5, we're going to be ready to do our restricted domain. We know that the smallest that we're going to allow x to be is 0, and that would be in the situation where you don't have a square at all, that you're rectangle only. And then the largest that you could be is if you're square only. And so if you're square only, then there's no rectangle. And if there's no rectangle, then that 4x is the entirety of the 24 inches. And so x, if you divide by 4, is going to have a maximum of 6. Okay. So just as a note on this, the x equals 0 is if we're rectangle only. And the x equals 6 is if we are square only. All right. So that gives us our interval of interest. X cannot be bigger than 6, or I just can't get that 24 as my perimeter here. So I do have a solid maximum and a solid minimum value here. Now we're ready to go into some derivatives. So let's look at the first derivative. So this is a function. I didn't write it in function notation up here. It's an equation, but you can just imagine an of x. It is a function of x right there. And so its derivative is, let's see, I can use the chain rule on the second part. So we've got 2x plus 2 times 3 is 6. Times negative 1/2 x plus 3 to the first power times the derivative of negative 1/2 x. So that's going to simplify to 2x minus 3 times negative 1/2 x plus 3. I can leave that alone for now. And then step 7 is our first order critical values. So we want places where the first derivative equals 0 and places where the first derivative fails to exist. And it's polynomial, of course, so there will be none of those. Let's look for places where the first derivative is equal to 0. So now we'll finish that distribute. So 2x plus 3/2 x minus 9 equals 0. So that's going to be 4/2 plus 3/2 is 7/2 x equals 9. So it's going to be an x value of 18/7. That's my first order critical. I only have one. And just to confirm, it needs to be less than 6, but it is, because 42 would be your upper limit for sevenths. So I do have a first order critical value in the interval. Once we have that first order critical value, we're going to go and do some testing. All right, so we've already used the test for absolute extrema and the second derivative test. So just for fun, we'll use the first derivative test. So I just want to partition the domain into intervals, and so we'll do test intervals. We'll get some test values, we'll get some sign of the first derivative, and we'll get increasing, decreasing. So the restricted domain was 0 to 6, so we're going to separate this to 0 to 18/7, and then 18/7 to 6. So something in the first interval would be 1, something in the second interval would be 3, and then I can plug those into the first derivative. Okay, so into the first derivative, If I plug in 1, let's see, I will have, so that's 2, if that's 1, I'm just going to plug it in my calculator and not think about it. Stay. Okay, so I would have 2 times 1 minus 3 times negative half of 1 plus 3. So it gets a negative. And then if I plug in 3 instead, it's a positive. So I had a negative for 1 and a positive for 3. So it was decreasing and then it was increasing. Okay. So this one is going to be a minimum. All right. Now, it did ask me to find both a maximum and a minimum. I've only found a minimum. Now, since I want both, I am going to go back and use a test for absolute extrema. It's the only way to get both, but I hadn't done this one yet, so I went ahead and did it. So we're actually going to redo part 8 just to use that test for absolute extrema. So this one was part C. We're going to do it with part B because we didn't get a max. We only got a min and we needed both. So back to our A function. If we do A of 0, A of 18/7 and A of 6. That's the only way I'm going to get a max out of this one. Okay, so 0, where's my A function? Way up here. If I plug in 0, I'll have 0 plus 3 squared times 3, so that's 27. If I plug in 18/7, I'm going to have to go do that. I get 18/7 squared plus 3 times negative a half of 18/7 plus 3 squared. I get 108/7, which is approximately 15 point something, 15.4 say. That's only for my reference. And then plug in 6. So if I plug in 6, trying to plug in 6 quickly here, plug in 6 and I get 36. Okay, so we have our minimum. So our minimum was, again, that's the smallest in 18/7. Thank goodness it's a minimum because we already expected it to be a minimum from the first root of test. Now we also have our maximum found. Okay, so we're going to have a minimum for, we're going to have to get some dimensions up here for step 9. I'm going to go sideways. That's where I've got my space right here. So for step 9, we're going to have a minimum if x is equal to 18/7 inches, comma, I also want to know, that's only x, I want to know what L and W are as well. So remember W was negative 1/2 x plus 3. So let's figure that part out to find W. So W equals negative 1/2 of 18/7 plus 3, which is 12/7. And L was 3 times W, so I need to take 3 times 12/7. And that is 36/7. All right, so I've got that written down. I'm going to flip my screen again. So I have a minimum if I have a length of the square, 18/7, length and width of the rectangle, 12/7 and 13/7 inches. Minimum of 108/7 square inches. So that's the first part. Then for the other part, I have a maximum if, and so x is equal to 6 inches, and if x is equal to 6 inches, remember that if I plug 6 in for width, 6 times -1/2 is 0, so I have length and width of 0. So this is the square only case. So I have length and width of the rectangle of 0 and of 36 square inches. Those are our two answers for when we have both a maximum and a minimum.